Hello class, welcome to this video on the EOC review practice. So we're going to cover the problems in order to prepare ourselves for the EOC. This is going to be part one of part three out of three parts in the series because each of these videos are going to be substantially long, because if you look at the guide here, it's about 37 pages worth of questions and there's about 4 to 5 questions per page roughly. So we're going to try to break it up so that there's, about 13 pages per part here, 12 to 13 pages. Now for the guide here, this review guide, there is, if you have the Pearson textbook or you use it, all the lessons are labeled on there so that you can see where which lesson corresponds to which standard. There's a lot of standards here, at least, if you were to count them, at least 30 it seems, and they're broken down by percentage as far as relevancy to the EOC. So we got most of the standards are in yellow, 46%, congruence, similarity, right triangles, and trig, and then you have the second most being on circles and measurements, and then you have a little bit of modeling with geometry. So let's go ahead and get started. We're going to be focusing on the first category, but we're going to finish off the second category in another video. If you look at the page here, this is just a reference page. This is the only reference sheet that you're going to have on the actual EOC. This is it. You got a bunch of conversions, a few formulas, and that is it. So you're going to need to know a lot of the stuff or remember a lot of the stuff that we talked about. So the first standard here, no precise definitions of various terminologies here based on talking about point, line, distance, and all that. So number one, we have given x, y, and z, w intersect at point A, which conjecture is always true about the given statement. Okay, so we know that line x, y, and z, w, so let's go ahead and draw them. So suppose this is line x, y, and this is line ZW. So we got X, Y, Z, and W here. And they intersect at point A. So here's an example of this. There's multiple ways that you can draw this, right? You can draw it like that, right? There's multiple ways that you could do it. So for part A, XA equals AY. So are they saying that they're saying that these have to be equal to each other in that statement? This is not necessarily true. They don't say anything about where A is on the line. In fact, if you look at this, graphic here, it's not, A is actually closer to X than to Y. You could have drawn this either way. It could have been closer to Y than it is to X. So this is not always true. It's only true in certain circumstances. Angle XAZ is acute. And in fact, it is acute here, right? But I need not draw it like that. I could have drawn it, I could put X in here, right? I could put X there and Y there, and that's still the same line. That's still line XY. But now XAZ is obtuse, right? So I could easily switch these and it would be false. So this is not always true. XY is perpendicular to ZW. So we got XY. This line is perpendicular to this line, which means that this has to be a 90-degree angle. But that doesn't have to be true. In fact, in this case, it's not true because it's obtuse. So this is false as well. X, Y, Z, and W are non-collinear. Non-collinear means they are not on the same line. Okay, so X, Y, Z, W, that is collinear. Non-collinear means one or more are not on the same line. And that is the case here. These 4 points are not on the same line, and therefore this is true. All right, so number 2, the figure shows lines R, N, and P intersecting to form angles, and the numbers are shown there. All 3 lines lie on the same plane. Based on the figure, which of the following individual statements would provide enough information to conclude that line R is perpendicular to line P? Okay, so if line R is perpendicular, that means it's at a 90-degree angle. It's a right angle to P. So we want to show that that's the case. Well, if that's the case, then that means that this has to be a right angle here. All right? And if that's a right angle, if we want to show that that's the case, right? Which statement would show that? Well, we know that that has to be true, and that means that this would have to be true, right? That angle would have to be right angle. This would have to add up to 90. This would have to be 90, right? So that means if this has to be 90, that means 1 and 2 have to add up to 90. So let's go ahead and write that statement here. So we got angle 1 plus angle 2 has to add up to 90. Well, if angle 1 and angle 2 have to add up to 90, then that means angle 2 cannot be 90. So this is already false, right? Unless angle 1 is 0, which, you know, we're not assuming that it is because we have an angle here. It actually exists. It's not 0. All right, so for the next one, angle 6 has to be 90. Well, we know that if this is equal to 90, right, then this has to be 90 because this is a linear pair. And so this has to be 90. So that's true. So we know that the measure of angle 6 plus all of this, right, has to be 180. And therefore, this has to be 90 because this is 90. All right, so that is true. Let's look at 3 and 6. Okay, so measure angle 3 has to equal measure angle 6. Well, yes, that is true. It is true that angle 3 is equal to angle 6. However, does that necessarily show that it's perpendicular? And I would argue no, it does not show that you cannot conclude that it's perpendicular based off of that statement, because this just as well be 45 degrees and that be 45 degrees, and that would still be a true statement. 45 is equal to 45. All right, so and then that would show that it's not perpendicular. So this is not always true, right? So even though this statement itself is true, it's not enough information to conclude that it's perpendicular, rather. All right, so 1 and 6. So if 1 and 6 add up to 90, so if this adds up to 90, that would not show that R is perpendicular to P. That would show that N is perpendicular to P, right? Because N would now be at a 90-degree angle to P. So this is for line N perpendicular to line P, not R. So then that's false. 3 and 4 equal to 90, same deal. That you can use that to conclude that this is true. 4 and 5 add up to 90. So we got 4 plus 5. And yes, if that's a right angle, then that means that this R is at a right angle to this P, right? So you can conclude that line R is perpendicular to line P. So yes, we are going to select that. All right, so number 3. Which of the following are true about the points on the number line? So we're going to go ahead and list out all of these values here. So let's go ahead and find AB. Now AB you can find by counting the number of jumps, or by subtracting. You could do 0 for B minus -4 for A. And if you did that, you would get 4. So either way, you're going to get 4 for A. If you did AC, for instance, and you would have to count the 4 steps here and then an extra 3 steps for a total of 7. Or you could do 3 minus -4. And then if you wanted to do, we have AB, we have AC, we do need BC. So BC is 3 here. We do need CD, which is 1. All right. And let's see here, AB, AC, BC. We do need AD, and AD is a total of 4, 3, and 1, which is 8. And I believe that is it. So we got everything that we need. Now we can plug it in to this, to these equations. So if I plug it into the first one, I would get 4 plus, so 4 plus 3 is equal to AC, and AC is 7. And that is true. This is a true statement, so we're going to select that. CD plus AB, CD is 1, AB is 4, is equal to BC, which is 3. This is not true, so we're not going to select that. We're just going to say false. CD is 1 is equal to 1/3 times AD. AD is 8. Now 8 times 1/3 is 8/3, and 1 does not equal to 8/3. So I can just change this and change it to an 8/3, and that's not true. 1/2 times AB. AB is 4, so half of 4 is 2. And then we got CD is 1 plus BD. Oh, I knew I forgot something. BD. So BD is this 3 plus the 1, which is 4. Okay, so we have that. So 1 plus 4 divided by 2, which is 5 divided by 2, and 5 divided by 2 is not the same thing as 4 divided by 2, so that's false. All right, so 1/3 of AB, we'll do it over here. 1/3 of AB is 4, and then you got CD, which is 1 plus BC, which is 3 over 3. And this is 4 over 3, and that's 4 over 3, so this checks out. So that's true. And that is it for that question. All right, so for number 4, given that the measure of ACF is 70, so this angle, right, this entire angle is 70 degrees. If ACB is 16, so ACB, that right there is 16. Well, if that's 16, then that means this is 16 because these are the same angle right there, right? They show you, they indicate that it's the same angle. What is BCD? So you want to figure out what BCD is. So you want to figure out that one. Now we know that that angle is the same as this angle. So let's call it X. They're both the same angle, so we can call it X. And we know that all of these angles here should add up to this big angle, which is 70 degrees. That's called the angle addition postulate. So that means we can add up these angles. We can do 16 plus, so we could do 16 plus X plus another 16, and that has to equal to 180. And there you go. And so we'll go ahead and solve that. So we get 2x here, and then that's going to be 32. So we got 32 plus 2x equals 180. We'll subtract 32 on both sides here. We get 2x equals 148. And then we can cut it in half. Oops, I said 180. I'm sorry. Not 180. 70. I'm being silly here. 70. There you go. Sorry about that. So it's 70 minus 32, which is 48. Not 140, not what I said earlier, 48. And then divide that by 2. And you get x is equal to, let's see here, it's going to be 24. And we'll see if that makes sense. 24 plus 24 is 48. And then 48 plus, no, that's not true. This is 20, no. 38. Sorry about that. Making a lot of silly mistakes here. So this is 19. And then 19 plus 19 is 38. 16 plus 16 is 32. 32 plus 38 is 70. So this checks out. This is why you want to check your work because, you know, especially for someone like myself, there's, you know, I make a lot of silly mistakes like that. And then you want to see if it holds up to the situation. All right, so now we know that x is 19, and therefore this is 19, and so CBD is 19. So we can say that this is the measure of angle BCD, rather, is 19. All right, so number 5, what is the best description of an acute angle? So it's just a definition question. So an acute, so this is acute, right? And then you have acute, then you have right angle, and then you have obtuse, right? And you have some other angles there, but these are the main ones. Acute is smaller than a right angle. So this is a right angle, which is 90. This is smaller than 90, but greater than 0. So it's between those two. And then, so 0 is just flat, right? And then you have that, and then you have this, and then this is greater than 90, but less than 180, right? 180 would be a straight angle. So it's an angle that measures more than 0 but less than 90. Number 6, what is the name of the angle formed by BA and BC? So these are rays, right? So BA is a ray. That's BA, that's my ray. And then I got a ray known as BC. And if I put those rays together, right, then B has to join B because they're the same exact point. So there you go, then that's ray BC. So BA and BC, there's my angle. It's angle ABC, or CBA. Looks like we got ABC right here. There's our answer. All right, so the next standard, we're going to represent transformations in the plane, describe them as functions, and compare them to preserve distance and to angles. Okay, so that compare transformations that preserve distance and angle to those that do not. So, okay, so all about transformations here. -7, 4, the point -7, 4 is reflected over x equals -3, and then the resulting point is reflected over y equals x. Where is the point located after both reflections, both transformations? So we got -7, 4 is being reflected. Okay, so these are our lines here. They kind of got us set up here. So this is x equals to -3 right here, this line. And this is y equal to x. So we want to do this reflection. Remember, a reflection is when you're the same distance from either side of this line of reflection here. So we got to count that, and that has to be the same. So this is 1, 2, 3, 4 spaces, and so it's going to be the same on the other side, 1, 2, 3, 4 spaces. And that's my new point right there. And that point is 1, 4. So that's my ordered pair. And now I'm going to reflect it about y equals x. So it has to be the same distance here as it is here, right? So you can either do it like that as a good judge. So maybe it's like around here or something like that, or maybe it's actually closer to like over here. It's kind of hard to do it when it's y equals x. So I would suggest using the rule. This literally says y is equal to x. So that means y is equal to x and x is equal to y, which means that this y value is now going to be the x value. So y is now going to be 1 and x is now going to be 4. You just basically swap them. And so you swap them and then you get, so if you wanted to take 1, 4 and reflect it about y equals x, then that's going to be 4, 1. So the rule for that is if you take a coordinate and do this rule, then it's going to turn into yx. All right, and so 1, 4 is going to be 4, 1, 1, 2, 3, 4, and 1. So it's about there. And if you see that, that kind of makes sense, right? So it's about the same distance on either side of that. So we got 4, 1, and there you go. There's my new coordinate. So we are going to choose that. All right, so number 2. Given AB with coordinates A, -3, -1, B, 2, 1, and then we got A prime, B prime with those coordinates. Which translation was used? So we want to figure out what translation was. We know it's a translation, it says it. Translation is when you're moving things, right? You add the same number or subtract the same number to the x, and then you do it to the y. So I want to figure out, well, how do I get from -3 to -1? Well, I just subtract them, right? So I could do -1 minus -3. And if I did that, remember it's final minus initial, right? So it's where you end up minus where you started. So -1, this is a double negative, so it's a positive. So -1 plus 3 is 2. So that means I got to add 2 to -3 to get to -1. And then if I wanted to get from 1 to 2, I subtract those. I get 2 minus 1, which is +1. And so, I'm doing the wrong one, sorry. From here to there, -1 to 2. So I got to subtract those. 2 minus -1. This is a double negative, which turns it into a positive. So if I take my A, right, and I undergo a translation, which we'll call T, 2, 3, this is +2, this is +3, I basically add 2 to -3 and 3 to -1, then I will get the solution that I got here, which was -1 and 2. And so that makes sense. So that means that's my translation. It's you add 2 and then you add 3. So the rule is add 2 to the x, add 3 to the y. And that does work for B as well. 2 plus 2 is 4, and then 1 plus 3 is 4. All right, so there's my rule. For the next problem, number 3, it says point F prime is the image when point F is reflected over x equals -2, and then over the line, y equals 3. The location of F prime is 3, 7. Which of the following is the location of point F? Okay, so let's go ahead and draw this out. It's easier to draw it. But first, what I'm going to do is I'm going to kind of show you what's happening here. So we don't know F, right? So that's an unknown. So I'm going to go ahead and label it here. F, we don't know the coordinates for F. However, we do know that it undergoes 2 transformations, right? It says, So well, let's call this f double prime. They call it f prime, but let's call it f double prime. So the location of f double prime is 3, 7. The reason I call it double prime is because it's undergoing two transformations. There's a reflection over x equals -2, and then a reflection over y equals 3. So there's two transformations that I want to write down. Okay, and that'll be f double prime, which is the final coordinate they told us is 3, 7. Now, it says this is the image when f is reflected over x equals -2. So we got a reflection over x equals -2. And we'll call that f prime, and then we don't know what the coordinates for that is yet. And then it undergoes a reflection about y equals 3. And that's really the diagram of what's going on. So that means if I wanted to go to f double prime back to f, I need to go travel backwards, right? So I need to travel backwards here. So I need a reflected about y equals 3, and then I got a reflected about x equals -2. So hopefully that diagram helps. You have to go backwards, right, and do the reverse. So we have to do y equals 3 first. Let's go ahead and draw this out. So we'll do the best we can. We'll just kind of draw a quick diagram, nothing crazy. 1, 2, 3. Okay, that's 7, that's 3. So let's reflect about x equals -2, or y equals 3, sorry. So y equals 3 is a horizontal line. Remember, y equals is a horizontal line. And then x equals -2 is a vertical line. So that's x equals -2 right here. That's vertical. And I'll actually color code that. So that's going to be red here, which is going to be this part right here. So that way I don't get confused with the, because they're in different colors here. So let's do y equals 3. So if we have 3, 7, and that's f double prime, I'm going to reflect it about that, which means the distance is 1, 2, 3, 4, 5 spaces on the other side, right? So 1, 2, 3, 4, 5 spaces. So this is -2, -3, -4, -5, -6, and -7. So now it's at -7, but the y value is still going to be 7. So this is my f prime. This is what it was before reflected. And I said I wasn't going to do about the red, and I end up doing about the red. I got to do about the blue. Sorry, the blue. So this is f is how much away from the blue? 1, 2, 3, 4. It's 4 spaces away. So that means it's got to be 4 down. 1, 2, 3, and 4. So it has to be at -1, but still at an x value of 3. So it's going to be right here, and that's going to be f prime. Sorry about that, the little mistake there. I'm glad I caught myself. So we got 3, -1. All right, so now we reflected it about y equals 3. Now let's reflect it about x equals -2. So let's do that now. It's 1, 2, 3, 4, 5 spaces. That's what we said earlier. And then it goes 5 to the left here. 1, 2, 3, 4, 5. And it's still going to be at a y value of -1. So it's going to be right over here. So now we know what f is. F is -7 and -1. There you go. There's my answer. So now we can fill in our diagram. This is 3, -1, and then this is -7, -1. And we got our final result. Okay, so for number 4, triangle JKL is rotated 90 degrees about the origin and then translated by using that rule. What are the coordinates of the final image of point L? So we're interested in just L. That's it. So let's focus on L. What are the coordinates of L? Well, the coordinates of L are, you got to be careful here. These are going by 2s, 2, 4, and then 6. And so that means that, all right, so that means that this has to be an x value of 5, and this has to be a y value of -1. All right, so the coordinates here are 5, -1. So they're trying to trick you there. Just be careful with the scale. So that's L. And it's going to undergo a rotation of 90 degrees about the origin. Okay, so that's O for origin there. So what's the rule for that? Well, the rule for 90 degrees, rotating 90 degrees about the origin, is you take your xy, and once you get xy, you basically swap the coordinates, and then y is now going to be negative. And if you think about that, makes sense. If I had the coordinate 3, 1, and I rotate it 90 degrees, then that means it's got to be at a 90-degree angle. It's got to be rotated. So it's going to be something like that, right? And so notice that the coordinates are not the exact same. This is actually a little bit higher, and that's because we swapped the xy to make it yx. And then it's negative x, right? This is a negative x, so a negative value here. So therefore, the first coordinate is going to be negative. Okay, so that's how I kind of remember. And this is 90 degrees counterclockwise, right? That's what they didn't really specify, but we're assuming that they mean counterclockwise. Because if it's positive 90, positive is counterclockwise. All right, so there you go. There's my rule. So let's use it. So let's swap the 5, and this is x and this is y. So let's swap it to get L prime. And then that'll be -1 and then 5. So we swapped it now, but then this has to be, there has to be a negative in front of it, and double negative is a positive. So really this just becomes +1. All right, there you go. That's my rotation. And now we are going to do a translation, which is t. We gotta change x by -8. We just got to subtract 8. And we got to change y by 5. So that's what this notation stands for. All right, so we're going to basically add or subtract 8 from 1. So 1 minus 8, and then we got to do 5 plus 5 using those two numbers there. And so we get L double prime is -7 and 10. There you go. We got it. So that's how we translate and rotate. A transformation takes point A to point B. Which transformation or transformations could have led to this? Could this be? So okay, so we got F is a reflection, R is a rotation, and T is a translation. We want to get A to B. That's all we care about. We want to go from A to B. Well, and so what we could do is we could physically move A to B, and that would be valid, and we'll call that transformation T. And so T is true. You can get from A to B using a translation. You could also do a reflection, and you could reflect about this, right? Because it says here that AB is actually perpendicular, so it's at 90 degrees, and AC is equal to AB. So we rather right here, AC is equal to AB. Well, if AC is equal to AB, that must mean that this is equal. But that's called the perpendicular bisector theorem, or the it should be the either the converse or the regular perpendicular bisector theorem, one of those. But in any case, that's true. And so if that's the same distance, that means we could take a reflection and reflect it from A to B. We can fold it. So yeah, we could do a reflection. And finally, we have R. We can do some kind of rotation about O. And is that true? Well, we know that the distance that says here AC to CB. Well, we know that this is the same distance as that, right? That they said that as such. And therefore, by the perpendicular bisector theorem, because we know that this is a perpendicular bisector, right? That must mean that from O to A has to be the same distance as from O to B. So this is actually the same distance. And basically, if that's true, that means that this is a radii. That's a radius. And so you can think of it as a circle with a radius r. And therefore, you could rotate to go from A to B. And so this will be true. Yes, you can do a rotation and get from A to B. So yes, this is true. So you can do all of these. This is a little bit tricky, but there's some theorems there that are actually kind of hidden in there that you want to kind of use. But that is the final answer. Okay, so pretty interesting problem there. So the next standard, given a rectangle, parallelogram, trapezoid, or other regular polygon, describe the rotations and reflections that carry it onto itself. This is all about symmetry and those kind of transformations, right? Rotational, symmetry, all that. So which transformation will place the trapezoid onto itself? Okay, so, well, let's go ahead and see if this works. Counterclockwise rotation about the origin by 90. So we're going that way. Well, if I take this, right, and I rotate it 90 degrees, well, that means that I'm going to take this and I'm going to rotate this line right here that connects that point about the origin at a 90-degree angle. So I'm going to draw a 90-degree angle to that. See, that's about 90 degrees, forming that L shape. And if I did that with the same distance, you can see it's not going to be at the same point. So it's actually, so if I rotated this whole trapezoid, it'll actually be, you know, probably more like that, right? If I rotated it 90 degrees. Sorry, the picture's not very good, but you get the idea. This is the part that flares out. So yeah, this is not going to be true. You can also use the rule. Remember the rule for 90 degrees about the origin is you take x, y, and it becomes negative y, x. So if I did this and I swap them, I get negative 3, 2. So I would actually be like over here, basically what I was saying earlier. Okay, so that's false. Not true. All right, so next one is rotation. So if I want to rotate about 180 degrees, I'm basically going to do 2 of these, right? 2 of those 90-degree rotations. So if I take this and I were to do another rotation, I would just switch the coordinates again, and then put a negative in front of that. So there you go. So this is my rule for rotation 180 degrees. So if I did that, well, this will turn into negative 2, negative 3, which is definitely not this, right? So therefore, it's not going to solve the problem by rotating it another 90. Reflection about across the x-axis. So if I reflect this line across the x, well, then that's just going to fold it over here. It's not really going to do anything. It's actually going to fold it so it's going to be at 2, negative 3, right? Where it's the same distance here as it is here, which is not that coordinate. And then finally, if I were to do the last one, that would work. If I fold it along this, then I would get the same coordinates. It would be negative 2 and 3. You can see that this is a line of symmetry, and so if I fold it along there, it's going to meet up nicely. All right, so number 2, which transformation will carry the rectangle shown below onto itself? So if I take this line, fold it along that little crease there, will this go onto there? And the answer is no, it will not. And that's because if you ever tried folding a rectangular piece of paper along its diagonal, it's actually not going to fold onto itself like you would think. You know, if you did this by, if you actually did this, it's not going to fold along itself. And that's because it's not really a line of symmetry, right? It's so what really happens is that this point, right, has to be the same distance from here, and so it has to be like around there somewhere, and so now these are the same distance away, and so this is going to fold along in this direction. So if I fold this, it's actually going to go more along the lines on the closer to this side than it is even to there, right? So this distance here is going to actually fold along there. So that is not going to happen if I reflect it over line M. So this is not true. Now, if I reflected about y equals 1, y equals 1 is a horizontal line. Now, that is an actual line of symmetry, right? Because this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this is actually a line of symmetry. And therefore, if I fold it along that, then it will fold in nicely. Just folding it in half, I guess you can say this hot dog style, and that would work. So we got the reflection about y equals 1. If I did rotation 90 degrees, if I rotated this 90 degrees, it would kind of look like this. So that's not true. And then if I rotated it another 180, which is a total of 270, it would actually look pretty similar to that. So there you go. It's not going to work any other way. All right, so for number 3, which figure has 90-degree rotational symmetry? So if I look at a square and I want to figure out the rotational symmetry, well, the way I think of it is you start in the middle and break this up into some pieces here. Now we know that for a square, these are all the same length. So these are all identical pieces. So if I were to take this piece and rotated it, I would get this piece, right? So that means I would have to rotate it, well, since these are all identical, it would be 360 divided by 4 pieces, which is 90. So we know that for a rectangle, the diagonals are perpendicular. And that makes sense here. So if I rotate this 90 degrees, I will get from point 1 to point 2. Rotated it another 90 degrees, I get that, and so on. So this has rotational symmetry. If I were to do this for a regular hexagon, then I would have to break it up like this, right? and these pieces are all identical. But if I wanted to move from 1 to 2, for instance, I would have to, well, I have total 6 pieces, so it would be 360 divided by 6, so it would have to be 60 degrees to move from one to the other. So this is not 90-degree rotational, it's 60 degrees, okay? All right, equilateral triangle is actually going to be 120 degrees if I were to break this up kind of like this. Then to get from here to here, I would have to rotate it 120, 360 divided by 3, and so on. Number 4, select all the polygons to have rotational symmetry. This is similar to the square 90-degree rotational symmetry there. Now for part B, there is no way that I can do this, right? Because this is not even the same length as this. These could be the same length, but this is not even the same length. And so if I rotate this way, if I take that and I rotate it 90 degrees or something like that, from here to there and just rotate it 90 degrees, then it would kind of look like, I'll try to show you. Let's see, from here to there, it would kind of look like this, right? It would kind of look like that if I were to try to rotate that, which definitely does not line up, right, with itself. So, and if I try to do this 180, then it's going to look like that, right? If I did a 270, it's, you know, it's not going to line up. The only way to line up is if it's a full 360. So this is not rotationally symmetric here. For C, just like what I said earlier, I can rotate this. This is a pentagon. If I rotate it by 360 divided by 2, then this will work, right? That would actually rotate from one to the other. Or 360 divided by 5, sorry, 5 pieces, 5 triangles here that are equilateral, or that are all the same length, rather, dimensions. Now for D, I could rotate this. If I break this into these pieces, well, I know that these pieces are the same, that these 2 triangles, 1 and 2, are the same. So if I wanted to get from 1 to 2, I could just rotate it by 180. So yes. And then for E, the same deal. If I rotate this a full 180, then I would get the same shape. So yes, those are rotationally symmetric. Okay, so for number 5, consider the figure this onto the right here. So let's look at the figure. So this little star shape, I guess. Which of these apply? So is it rotationally symmetric or reflectionally symmetric with line H? And yes, this is a line of symmetry, so you can reflect it and that'll work. Same deal for line G. That's a line of symmetry, I can fold it and it'll work. Same thing for line M. That's a line of symmetry, I can fold it and that'll work. Now it will not work for line N, right? Because that's not a line of symmetry, so it will not fold nicely. So it's H, G, M, but not N. Is it 90 degrees rotationally symmetric? Well, if I start in the middle here, I can only rotate to go from 1 to 2. I have to rotate this, well, this 3 pieces here, so it's 360 divided by 3. I'd have to rotate it 120 degrees to get from 1 to 2. And then another 120 to get to there, and then another 120 to get to there, for a total of 360. So this is 120 symmetric, but not the other ones. All right, so let's move on to the next one. Definitions of rotations, reflections, and translations in terms of angles, circles, perpendicular lines, parallel lines, and line segments. Okay, so if triangle ABC is rotated 180 degrees about the origin, what are the coordinates of A prime? Okay, so this is 180 degrees. So if it's rotated 180, we said that the rule is that it basically converts xy to negative x, negative y. So that's exactly what we're going to do. Coordinates of A are 5, 4, so that's going to convert into negative 5, negative 4. So A is going to go into A prime, negative 5, negative 4. B is currently 3, 4, so it's going to turn into negative 4, negative 3, negative 4. And then finally C is 1, 1. So it's going to be -1, -1. And that is it. Those are the coordinates. And you just want A prime anyways. So, but I did it all for all of them just so you can practice. Look at it. Number 2, what is the image of M, 11, -4 using the translation? So we're going to subtract 17 from X and add 2 from Y. So that's all you got to do. Take that and do that transformation. 11 minus 17 and then -4 plus 2. Which is -6, -2. There you go. Number 3, write the rule for the translation that takes 3, 2 to 2, 6. Well, then you just got to subtract these. So you got 2 minus 3 is -1, and then 6 minus 2 is 4. So that means the translation rule is -1, 4, which means you subtract from x. So that means it's going to be xy maps to x minus 1, y plus 4. And there's my rule in arrow notation. Number 4, which the triangle QRS has those vertices, is rotated 180 clockwise about the origin. What are the new coordinates of triangle Q prime, R prime, S prime? So rotation by 180, we know that rule, right? So rotation by 180 takes xy, converts it to -x, -y. So that's pretty straightforward. So Q is going to go to Q prime, and it's going to be 2, -4. You just swap the signs there. R is going to go to -2, -2, swap the signs. And S is going to go to S prime, swap the sign. 0 doesn't have a sign, so you leave it like that. And then -2 swaps to 2. And there you go. All right, and then the last one for this, or last couple of ones for this section. The graph of a figure and its image are shown below. Identify the transformation. All right, so what's going on? So what's going on to go from this here to that? So you can kind of see that you literally have to just slide it. So that means that's going to be a translation. You just slide it. Okay. And here, this looks like a, so if you look at this, if I were to take this R right here and I rotated it, then I would get that, right? If I were to take this here and I rotated this C prime the same amount, if I were to rotate it, I would get C right there, or C, or I had to go the other way. I had to go from here to here, and then from here to here. And then if I were to take this S and rotate it that way, then that's a rotation, right? I have to rotate it. Now, it can't be a reflection, because if it's a reflection, this will work. This will actually flip here, but then this would actually flip to over here. And that, so it can't be a reflection. It has to be a rotation. For this one, the last one, for this question here, this definitely looks like a reflection. If I reflected it about here, then this will go here. This is the same space as it is here. Same deal here. So this is definitely a reflection. And then this one right here, if I were to take this, let's see here. If I were to rotate this, then notice that these are already kind of aligned. If I were to rotate this, then the only way that I can rotate this is H would have to be down and D would have to be up. There's no other way about it. If I rotated it this way, then D will still be up. And the only way that D will be down is if I rotated this all the way. And in that case, D would be down here, but H would be up here. And then it would still wouldn't look like this, right? So if you try to picture rotating that, it's not going to match up. So therefore, it has to be a reflection. You have to take this diagonal line. If I were to flip it around that diagonal line, it's the same. Flip it around there, it's the same. And there you go. So it has to be about that line, maybe y equals x, something like that. It's definitely a reflection. Okay. So for number 6, a line segment from 0, 0 to 4, 6. From 0, 0 to 4, 6 is reflected across the y-axis. what are the coordinates of the reflected line segment? So we got, it helps to just draw it. So you got 0, 0, and then you got 4, 6. It's around there. So there's my line segment. It's reflected across the y, so it's going to look like that. What are the coordinates of the reflected line? Well, this is still going to be 0, 0. And this time, instead of it being 4, 6, it'll reflect to -4, right? Instead of +4, it'll be -4, and it'll still be 6. So 0, 0, and -4. Okay, so it is -4, 6. I think this question actually meant to say the x-axis, not the y-axis. So there's a little typo there. If I reflected about the x-axis, then that's going to change things. Since this is like 6 away, it has to be 6 down. So that means it's going to be at -6, right, instead of +6. So it's going to be, in that case, 4, -6. All right, so just change that to x-axis there. So number 6 is C. All right. So for this one, the next one, we're talking about rotation, reflections, translations. Draw it using whatever tools you have, and talk about sequence of transformations to get from one to the other. So which transformation maps the solid figure onto the dashed figure? So what can we do essentially to get from one to the other? Well, if I were to take a line from here to here, notice that that's the same distance from there to there. And so if I were to take this and rotated it, flip it over that way, rotated it rather, then that would give me that figure. It's kind of hard to visualize that, right? But if I were to take this and do a 180, then I get that, which is exactly that line right there. And then if I were to take this and flip it 180, I would get something like that, right? And so, which is, or actually, I would have to do it like this. So if I were to do this, rotated it about here, 180, then it would go to this point right here. That point will go to here. And this point right here, let me do that as another color. From the origin, if I were to rotate that 180, that would actually go here. So you can kind of see, hopefully I can kind of convince you, if I take each line to each point and rotate it at 180, it's going to get to the point on the other side. And so this is a rotation by 180 degrees about the origin. Definitely not a translation because I can't just slide it to get from one to the other or glide it. Reflection across the x-axis. If I reflected about x, then it would look kind of like it would kind of look like that. Not a really good drawing, but it would kind of look like that, which is not this. If I were to reflect it across the y, then it would kind of look like that, right? And definitely not equal to the one in dashed. So definitely a rotation. Number 2, triangle ABC and DEF are graphed on the same set of axes. Which sequence of transformations maps ABC to DEF? Okay, so this is the pre-image, and that's the image. Okay, so if I take a reflection about the x-axis, so let's do that. If I reflected about x, this line here, then this is 1, 2 away, 1, 2, then that'll be over here. And this will be 1, 2, 3 away, 1, 2, 3. This is 1, 2, 3, 4, 5, 6 spaces away, 1, 2, 3, 4, 5, 6 spaces away, so it'll look like that. And then if I took that and reflected about the y, this is the y now, it's 1, 2, 1, 2, 1, 2. Hold on a second here. That's not 2, that's only one space. 1 and then 1. And then this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So yes, it would this would actually work. So it's A. Okay, so for number 3, a triangle has vertices at those coordinates. Which transformation will produce an image with those coordinates? So to get from one to the other. So let's see if it's a reflection. Reflection about the x-axis. Now the rule for a reflection about the x-axis, I'm just going to show you the rules, is if you're reflecting about the x, then only the y value changes to its opposite sign, right? So the y changes. So it's going to be x, negative y. Reflection about the y, only the x changes. So it'd be negative x and y. We already talked about rotation 90 degrees about the origin. We said that it would be negative y and x, and then and that's counterclockwise rather. And that's for this one. Clockwise, that means this is going to be negative 90. So negative 90 about the origin, the rule for that is different. It's actually the same rule as for 270 for counterclockwise. And the rule for that is going to be y negative x. Okay, so now we got the rules. So let's go ahead and do them. If I reflected this about the x, then the y is going to change to positive 1, which that is not the case here, right? So therefore, it cannot be a. If for b, if I reflected about the y-axis, x is going to change. That's going to change to positive, and that's true. It's going to change to positive. That's going to change to positive. There you go. We got our answer. It's going to be b. All right, for number 4, triangle has vertices at those coordinates. What are the coordinates of each vertex if the triangle is translated 4 to the right, 6 down? Okay, 4 to the right, 6 down. So you got to add 4 to the x, subtract 6 there. So a is now going to be negative 7 plus 4 is negative 3. 6 minus 6 is 0. So a prime is going to be negative 3, 0. Let's do that here. Add 4 here, take away 6 there. So b prime is going to be 8 and 3. Let's see which one works. So we got a prime. There you go. There's our answer. All right, and that's a way to kind of speed that up. So number 5, Ken stacked 2 number cubes. Each cube was numbered so that opposite faces have a sum of 7. So this is how a normal die works, right? Is that if this is 2, then the face on the opposite side is a number 5. So the one that you can't, the side that you cannot see there on that side is 5. 5 plus 2 is 7. And so if this is 3, the one on this side that you can't see is 4. Okay? And that's how it's numbered. So it says here, which transformation did Ken use to reposition the cubes from P to Q? So you want to go from there to there. Well, obviously you can see that this 6 got rotated this way. And so now it's like sideways, right? And so that represents that looks like a 90-degree rotation. You took the 6 and you rotated it 90 degrees, well then it looks like that. And then 180 degrees would be like that, right? And then 270 would be like that, and then a full 360 would go back to where it started. So this is definitely a 90-degree rotation for this top cube. You can see that. So rotate the top cube 90 degrees, and it looks like it's clockwise. It's not counterclockwise, it's clockwise. Okay, and then for the bottom cube, now it's kind of hard because you can't see it, but we know that the side that is opposite of that is a 5, right? So on this side is a 5. So if I rotate this a full 180, then that means that this is now going to be a 5, and on the other side is going to be a 2. And this, the opposite side of 3, is 4. So if I rotate that, flip that one whole half a circle, then this will now be a 4. So this makes sense. That means that we rotated the bottom by 180 clockwise. So there you go. So we 90 degrees clockwise, rotate the bottom 180. There you go. Number 6, in the figure shown, which composition of rigid motion will map one triangle into the other? So we just got to figure out the transformation here. If I do a glide reflection, remember a glide reflection is when you take an object, you reflect it, and then you translate it parallel to that axis. So it would go like, it would be flipped, and then it will be moved. And that right there will be a glide reflection, okay? So that's what a glide reflection is. So let's see if that works. If I were to take this and flip it, well, if I flip it, let's say I flipped it about there, then this would be down here. This D would be, so that'd be C, that'd be D, and that kind of seems okay. We have C and D there, right? And then B would be, somewhere like over here. If I flip it, sorry, it's not very good drawing, but it's like right there. I'm just trying to flip this the best I can. This would be down here. That would be C, D. This would be B, and then A would be like closer to here. So it'd be some kind of weird shape, some kind of shape like that. Okay, and so I get, A, B, C, D, just like that, and then I can translate it parallel. If I translate it parallel, then it had to be in the same direction. Now, if I did that, this wouldn't actually work, right? D would actually be higher up here, and C would be higher. Every point that I move would be higher. I mean, I could, And I mean, you would argue, well, I can move it this way and then down. But if I did that, that will no longer be a glide reflection. A glide reflection can only move in one direction. It can only be moved, in this case, right or left. And so there's no way that I can just do a glide reflection. I can do a reflection and then move it to the right and down. That would work. But that would be different, right? That would be a reflection followed by a translation. So that would be true. I can reflect it, so I get that same shape, and then I can move it to the right and down. That would be correct. Two translations would not work here. As you see, we have to flip it. Rotations will not work here as well. If you try to rotate it, there's no way you can align that to make it work. All right, so that is it for that section. All right, use geometric descriptions of rigid motions to transform figures and predict the effect of a given motion on a figure. All right, so, and then this is also about congruence transformations to see if they're congruent. All right, which transformations map the solid figure onto the dotted line figure? So we just got to describe the transformation. That's pretty straightforward. If you were to reflect it about some invisible line in the middle there, you can reflect it. It would actually match up nicely. So this will be a reflection. We'll call this line M. So reflection across line M. Okay. All right, so there you go. So select all rigid motions that describe the pre-image and the image shown. So how do I get from one to the other, basically? So if I were to take this here and rotated it 180, let's see if that's true, I get that. If I were to take this and rotated it 180, I'll get something like that. If I were to take this and rotated it 180, right? I had to take that, rotated 180. Well, if I rotated it 180, it looked like this, but this will correspond to being on that shape there. And then finally, or have a few more here. So if I take this, rotated to 180, then I would get this point here. Oops, this point right here. And then if I were to take this, rotated to 180, I would get a point that corresponds to right around here. And so I get something like that. And so you can kind of see it's the same shape as that, right? So there you go. So I could do a rotation of 180. That would be fine. That would work. I can, let's see, if I glide reflect it, that means I would have to reflect it and then glide it. If I reflect that, I get this. So definitely I get something like that. So it's definitely not going to work. If I rotated at 90 and then reflected across a line, okay, so rotated about 90, so if I take that, rotated it 90, then this would go here. If I rotated this by 90, then this would go like over here. Rotated this by 90. Let's see, this. Oh, I did it the wrong way. So this by 90, then this will go here. This by 90. Then we'll look kind of like that. Yeah, this will definitely not look like that shape. So if I were to physically rotate this 90 degrees, it'll look kind of like, kind of hard to visualize it here. Here, let me try to, if I take that, rotate it 90, get this. If I take that, rotate it 90, I get this. If I take this point, rotated it from here 90 degrees, it'll look a bit about here. And then I'll do a couple more points. That one rotated at 90. It'll look around here. And then this 90, we did that one earlier. Okay, so then it'll look kind of like, not a very good picture. But you get the idea. It's not gonna look like that. It'll look pretty weird. It'll look kind of like, it's kind of hard. I'm trying to visualize it to kind of show you. but it would kind of look like that, right? It would kind of look like that. And then if I try to reflect it, then it won't look like this. Okay, so it's definitely not going to look like that. And then, so we did this one, reflection across horizontal line. Let's do that one. So if I reflect it across horizontal, it'll look like something like that. And then a reflection across vertical. Hold on, I'm going to try to do it better. And this will go like over here. So it'll look kind of like that. And then if I reflect it about this vertical, it would kind of look like that. So it looks like it does work if I reflect it across horizontal and then vertical. However, for part D, they don't want you to do it. Okay, so this one will work. If I reflect it across vertical and then horizontal, that's fine. For part D, they want you to reflect across horizontal and then rotate it. No, that's not going to work. If I rotate this 90 degrees, it's not going to look like this, and we want it to look like this. So it's going to be A and E here. Okay, so there we go. Let's move on to the next one. Number 3, we got a triangle is congruent to triangle PQR. State which pair of sides are congruent. Okay, so for this one, we have to see if they're congruent. So if I could take one and map it to the other. Now notice that these are actually longer than some of these. If I were to take this, all of these sides are actually longer than this. So this is definitely not congruent to, this is not congruent to that. Okay, if I were to take this and reflect it, I would actually get that. So that's true. So these are congruent. And there's only one pair that's congruent. So we're going to leave it at that. So those are the ones that are congruent. And so that's a congruence transformation. And therefore, those must be congruent. A reflection is a congruence transformation. A congruence transformation takes the pre-image and gets an image that is congruent to it. So therefore, this is a congruence transformation, and therefore they must be congruent. That's the concept there. All right, number 4, vertices of triangle JKL have those coordinates. Under which transformation is the image not congruent? That means if it's not congruent, you have not used a congruence transformation. A congruence transformation, here are the list of some of the congruence transformations. Glide reflections, regular reflections, translations, those are all congruence transformations. Rotations, those are congruence transformations. Dilations are not a congruence transformation because they stretch the figure or compress it. Okay, so let's see. If it's a dilation, automatically no. Translation is a congruence transformation, so it cannot be that because it has to be not congruent. Counterclockwise rotation, that's a congruence transformation, so it cannot be that. Reflection, no. Dilation, yes. That is not going to be congruent if you stretch it. And there you go. That's the concept there. For number 5, which transformation will always produce a congruent figure? As long as it's a congruence transformation, you're going to get a congruent figure. This is a translation. So yes, that'll produce a congruent figure. This is a stretch in that direction. This is a stretch in that direction. This is a stretch. Those are all dilation type things. So it's not going to be those. All right, number 6, a figure undergoes a translation, reflection, and dilation. Will the image be similar to the original? Well, no, because we're doing a dilation. So no, because a dilation is not a rigid motion, right? Congruence transformation is also known as a rigid motion. All right, so that would be that answer to that. So the next one. Use the definition of congruence in terms of rigid motion to show that two triangles are congruent if the corresponding pairs and so on are congruent. All right, so those two triangles are congruent. That's what they said. Which of the following congruent statements are true? So if these are congruent, then that must mean that TR has to be congruent to AN. It also means that, let's see here, we have TI is congruent to AG, right? TI congruent to AG. That works too. any combination that you can think of, like that, RI, NG, stuff like that. In addition, that means that angle T is congruent to angle A, angle R is congruent to angle N, and angle I is congruent to angle G. So let's see which ones are true. That one, RI. Let's see, TI. Well, no, because we said TI was AG, so this is not true. Angle T is angle A, yep. Angle R is congruent to angle N, angle I congruent to angle G, and that is it. Okay, so that takes care of that question. So for number 2, the image after a rotation of 90 degrees is DEF as shown. Which statement is true? Well, if this is a rotation, then they must be congruent. And therefore, we can show that there's congruence. So notice that C goes to F, A goes to D. So if I were to rotate A, 90 degrees, I would get D. If I were to rotate B, I would get E, and I would get F, and so on. So this goes to A, this is to B rather, and C is to E. Let's see, or rather, I'm sorry, I got it the reverse. C is to F, and that's B. Okay, so that means that DE is congruent to AB. BC, which is this one, is congruent to EF. Not DE, EF, so that's false. AB is congruent to DE, not DF, so that's false. Angle C is congruent to angle E. We said angle C is congruent to, this is angle C. Angle C is congruent to angle E. No, it's congruent to angle F, right? And angle A is congruent to angle D. Yes, A goes with D here, so yeah, that's true. All right, so number 3, the triangle below can be subject to reflections, rotations, and translations. With which of the triangles can it coincide? All right, so there's actually a typo, and I believe there's a typo in this question, it's just a little correction that needs to be made. This here should say 7 and 2, okay? Not 2 and 7, because that wouldn't make sense for the longest side to be 2 and the shorter side to be 7. Okay, so what you need to know, bottom line, is that if you're doing a rotation, a reflection, or translation, you're going to get a congruent shape. And that's what we want, okay? This one cannot be it because it's not even congruent. That can't be it, it's not congruent. This can't be it, it's not congruent. If it's not congruent, that means it cannot have undergone these unless it went through those and a dilation, right? And so it has to be B. Okay, so that's it for the last one, or that was the last one for that one. For number 1, the next standard, explain how the criteria for the triangle congruence theorems follow from the definition of congruence in terms of rigid motions. So in the figure shown, what is the value of x? All right, so first off, are these triangles congruent? The answer is yes, because we got a side that's congruent, we got an angle that's congruent, and we got another side that's congruent. So these two are congruent by SAS. Congruence theorem. Okay, so they're congruent. So now what? Well, if they're congruent, then that means that these have to be congruent to each other, the 19 and the x minus 4. So we're going to set those equal to each other and solve. Add 4 to both sides, and you got your x value. Pretty straightforward. All right, so number 2. In the figure shown, what additional information is needed to show that the triangles are congruent by SSS? Well, we have an S, we have an S, we need another S, right? We need to know that. We got an S, we got an S, we need another S. So we need another side. We need to know that AC is congruent to FD. And then if we do know that, then they have to be congruent by SSS. For number 3, for 2 triangles with identical orientation, what rigid motion is necessary? Basically, to get from here to there, you need to translate. You need to move it to the right and up. So it's a translation. Number 4, given the information regarding triangles, those 2 triangles, which statement is true? All right. So basically it helps to draw the triangles out. So let's go ahead and draw them out. So we have here A, B, C, E, D, F, okay? And so let's see here, we got angle, so we know that A has to be congruent. In this case, if you look at the shapes, B has to be congruent to E, obviously, because they're in the same orientation. and C has to be congruent to F, right? Okay, so there you go. So looking at those triangles, is A congruent to D? Yes. B is congruent to E? Yes. BC is congruent to EF. That's congruent to that. There you go. So now, based on that information, so they don't actually tell us that A is congruent. They don't tell us that. Or no, not A. They don't actually tell us that C is congruent. So let me get rid of that C right there. All right, so let me get rid of that C. Again, sorry about the drawing there. Okay, so they don't tell us that. That's all they give us. They give us those three pieces of information. So the given information matches the Sas criterion, so the triangles must be congruent. No, they give us an angle, and a side. Angle, and a side. So it must be AAS, right? Not ASA. The given information matches ASA. No. Angles C and F are also congruent. And the answer is yes, these are also congruent. They must be congruent because the other two are congruent. And therefore, those other ones must be congruent. And then it could be shown by ASA. Now we can say that, okay, ASA, yes, we can do that. We could do AAS, but we can also do ASA if we knew that F is congruent to C, which it is. So there you go. There's my answer. Okay, so for the next standard, which statement must be used to prove that the measures of 4 and 6 sum to 180? This is all about theorems about lines, by the way. Okay, so for this one, I'm going to try to fly through this as quickly as we can. 2 and 4 are congruent. Is that true? Well, yes, they're congruent because they're vertical. 5 and 6, are those linear pair? Yes, but do they prove that 4 and 6 add up to 180? So let's look at that. We want to prove that 4 and 6 add up to 180. Okay, well, so if I want to prove that adds up to 180, well, then if I knew that those were congruent, okay, well, those are congruent, and then 5 and 6 form a linear pair. So that's not going to help us because, yeah, it's the fact that these are congruent and then 5 and 6 are a linear pair tells us nothing about that 4 and 6 add up to 180, unless you say that 2 and 5 are congruent, right? Because they're same side. Because they're corresponding angles, but they don't tell us that. So it's not that one. 4 and 7, are they congruent? Yes, 4 and 7 are congruent because they are corresponding angles. They said that. So if we knew that, that's okay. Angles 6 and 7 form a linear pair. 6 and 7, they do form a linear pair. And because of that, because 4 is equal to 7, and 7 is a linear pair with 6, that must mean 4 is also a linear pair with 6. Not really a linear pair per se, but what I mean by that is they add it to 180. They're supplementary, not linear pair, but supplementary. So they add it to 180. And therefore, 4 and 6 had to add it to 180. So yes, that's correct. That's how you can prove that. Number 2, for what value of x is f parallel to g? So we want these to be parallel. And if they're parallel, then that means that these must be congruent because they're exterior angles. These are alternate exterior angles. Alternate exterior angles must be congruent. All right, so 10x plus, so yeah, they are congruent by the converse of the exterior angles theorem. And what are they equal to? We got to figure it out. So let's set them equal and solve. Subtract 10x on both sides and then add 9 to both sides. And we get 14 is equal to 2x, which means x has to be 7. So there you go, 7 by the converse of the alternate exterior angle theorem. It's on the outside of the sandwich. Okay, so number 3. If angle 1 is congruent to 2, can you conclude that the lines are parallel? If these are congruent, then yes, we can conclude because if they're congruent, then that must mean they must be corresponding angles. And if they're corresponding angles, that means that this line is parallel to that line. So n has to be parallel to p. So yes, n and p are parallel because corresponding angles are congruent. All right, Peach Street and Cherry Street are parallel. Apple Street intersects as shown in the diagram below. If 1 is equal to 2x plus 36 and 7x minus 9 is 2, then what is angle 2? Well, these are parallel, and so these angles actually what they do is, well, they form a 180 pair, because if this and this add up to 180, we'll call that angle 3, then and angle 3 and angle 2 are corresponding, angle 3 is actually equal to angle 2. And therefore, since 2 is equal to 3, and 3 and 1 form a linear pair, add up to 180, that must mean that 2 and 1 add up to 180. So there you go. So we got 2x plus 36 plus 7x minus 9 add up to 180. So we got 2x and 7x is 9x. 36 minus 9 is 27. We'll solve this here real quick. And when you solve it, you get x is equal to 17. Just to quickly solve that. And then we plug it into angle 2. So 7 times 17 minus 9, and that's going to be 110 degrees. Okay, just trying to save a little time there. All right, so for this one, prove theorems about triangles and use theorems about triangles to solve problems. So for this one, we got some parallel lines and all that stuff as well. So let's give me a second and we'll start looking at this problem here. So for angle 2, it says angle 2 is equal to 60. Let's go ahead and figure out all this stuff. Well, if this is 20, then this is 20, right? So we know that much. Those are congruent. And if that's 20, this is 20. Why? Because they told us that these are parallel. And this is a transversal. So these are alternate interior angles. Alternate interior angles are congruent. So that's equal to 20. So that means I know now that angle 2 is 20. There you go. And now, let's see here. Similarly, I know that since these M and N are parallel, if I think of this as a transversal, this has to be equal to that. Those are corresponding angles. So that means this has to be 60. So now I know angle 4 is 60. There you go. And angle 1 and 60 have to be the same because they're vertical angles. So I know angle 1 is 60. And now because of the theorem for triangles, I can figure out what angle 3 is. Because 20 degrees, 60 degrees, and angle 3 have to add up to 180, right? So angle 3 plus, for this triangle, which I'll do in red, all the angles have to add up to 180. So plus 20 plus 60 equals 180. And therefore, I get that angle 3 has to be 100. So now we know all of them. So angle 3 is 100. Angle 2 is not 60. Angle 2 and 4 add up to 80. Yes, that's true. They do add up to 80. And angle 2 and 3 add up to 180? No. Angle 2 and 3 add up to 120. Angle 2 is 20? Yes, that's true. So there you go. Those are my answers. Number 2, what is the measure of angle B in the figure below? So let's look at angle B. This is just using the triangle angle sum theorem to add up to 180. Also, this is an isosceles triangle, so that means that if this is 62, this is 62. And so we can figure out this angle. So the measure of angle B is, these angles have to add up to 180. So it's going to be 180 minus those two. And if you did that, you're going to get 56 degrees. All right, so moving on to the next question. Use questions 3 and 4. They relate to this figure. Okay, so we'll use this figure for questions 3 and 4. What is the value of y? Well, if I want to get y, I need to add these angles to 180 for that triangle. All right, so let's do that. So y is equal to 180 minus 46 minus 51. If I did that, I get 83 degrees. So now we know what y is, and that's 83. Now, if that's 83, that must mean this is 83. And if that's 83, then I can add these up to 180 to get x. So x is equal to 180 minus 83 minus 38. And if I did that, I get 59 degrees. There you go. Okay, so it says, what is the value of x? So we know that these angles have to add up to 180 for a triangle. So let's go ahead and do that. 2x minus 33 plus 2x plus 15 plus 2x has to add up to 180. And so let's go ahead and solve this. So you get 2x, 2x, and 2x. That's a total of 6x. Minus 33 plus 15. Let's see here. Adds up to minus 18 is equal to 180. And then we'll go ahead and add 18, divide by 6. Add 18 and divide by 6. And you're going to get x is equal to 33. All right, so for number 6, in the triangle, angle y is equal to 48 degrees. Angle x is less than angle y. Write the sides of the triangle in order from shortest to longest. So it's easier to draw this. So we're going to draw this real quick. If I were to draw something like this, so that's triangle XYZ. Well, 48 is, the angle Y is 48. Angle X is smaller, which we can tell this is a tiny angle compared to this. This is an obtuse angle. So the angle Z is larger than angle X, and X is smaller than Y. Okay, so that means that if X is the smallest angle, right, then that means the side opposite of that has to be the smallest side. So YZ has to be the smallest. Okay? And if 48 is the second longest angle, then that means that the side opposite of that, which is XZ, is the second longest. So this is going to be the next longest one. And then finally, the side, since this obtuse angle, angle Z, is the largest angle, that must mean the side opposite of it, XY, is the largest. And there's your order. All right, so for number 7 and 8, we're going to use that picture there. What is DF? If the perimeter is 58, what is the length EG? Okay, so we know that by the perpendicular bisector theorem, if these two distances are the same, then that means this has to be a right angle, and this has to be cut in half. And so 3a has to be equal to a plus 6. So let's go ahead and do that. Let's set those equal. And if you solve that, I'm just going to solve that real quick. You get a is equal to 3. All right, so now we know a, and that'll help us with the perimeter. If the perimeter is 58, what is EG? So if let's go ahead and get these two sides. So if the perimeter is 58, then, and we know that these are the same, let's call these x. So then if the perimeter is 58, then that means the perimeter has to add up to all those sides, right? Has to be x plus all of this. And what is all of this? Well, it's a is 3, so this is 9. 3 times 3 is 9. And this is another 9. So this is 18 in total. So if I did x plus 18, that should add up to 58. So let's go ahead and do that. That means 58 has to be 2x plus 18, which means x has to be, well, has to be 20. 20 times 2 is 40. 40 plus 18 is 58. So these have to be 20. Okay. So if this is 20, then that means that we can figure out what this side is using Pythagorean Theorem, because this is a right triangle. So let's use Pythagorean Theorem here. This is the hypotenuse. So we got 9 squared plus y, we'll call that y. 9 squared plus y squared equals 20 squared. And that'll help us solve for EG. So y is the square root of 20 squared minus 9 squared. And I'll leave it to you guys to do the math there. You're going to get, let's see here, the square root of 319. So that's going to be the length of EG. Again, I'll leave it to you guys to do the math there just to save some time. Select all the statements that describe EG. So, okay, so let's describe EG. So EG is a median because it goes from one vertex to the other and it cuts that side in half. So yeah, it cuts it in half. It's an angle bisector. Is that true? Well, yeah, because this angle is the same on both sides because due to the, isosceles triangle theorem, all that, because this is an isosceles triangle. So yeah, it's an altitude because it cuts the opposite side at a 90-degree angle. It's a perpendicular bisector. We said that earlier, perpendicular bisector theorem. And it is a line segment, technically. So yeah, so that is true. So all of those are true. So number 9, let's look at the proof. So it says, shown below are the statements and reasons for the proof. They are not in the correct order. Which of these must be the correct order? All right, so we want to prove, so the given always goes first, right? So this has to go first. So this is definitely going to be up on top. So that's going to be first. So that automatically eliminates A and D. So it has to be one of these. And then what you're trying to prove always goes last, right? So you're trying to prove AB is congruent. So this goes last. This goes on the very bottom. And there you go. So we got 3. Oh, and the last one should be this one. Okay, so 3 and then 5. There you go. Just based off of that alone, you can say that this is the answer. However, we'll go through it real quick. So we know that that's first. So this is number 1, or this is 1, 2, 3, 4. There's 5 steps. This is number 5. This is number 1. The next one is, let's see here. If so we know that it's given. So AD is parallel. So AD is parallel. And AD is congruent to EC. So this is congruent to that. So what we want to do is we want to know that this is congruent. And so this has to be true. We need that for step 2. That's congruent. And then because of that, we know that if we look at the angles, we know that since these are parallel, these have to be congruent because of alternate interior angles. And now that we know that this is true, we can say by angle, angle, side, that they're congruent. And that's like the logical order of the steps. Okay, so that's why it's B. So number 10, the figure below represents a swing set. The supports on each side are constructed from 2 12 by 12 foot poles connected at the brace by the midpoint. Okay, so this is at the midpoint, so this is cutting this in half. So that means there's 6, this is 6 on each side. And then this is 5 feet right here. All right, so it says the distance between the bases is 5 feet. What is the length of the brace? Well, this is the triangle midsegment theorem that states that this, if this is parallel to that base there, which it is, then AB is half of CD. So if CD is 10, then AB is 5. Well, CD is, guess what, 5. So AB has to be 5 divided by 2, or 2.5. So each brace is 2.5 feet. And this is called the triangle midsegment theorem. All right. So we're going to wrap this up shortly. We're going to try to wrap this up in the next 15 minutes here. We're going to try to get through 2 more pages here real quick. So this is a parallelogram. So what is the measure of KSP? So KSP. So you're trying to figure out that angle right there. Okay, well, first off, we know that these are congruent. So let's call that X, all right? And we know that if this is, since these are parallel, because it's a parallelogram, that means this has to be congruent to that. So this is also X. So that'll help me find that angle. And since this is a triangle, it has to add to 180. So 76 plus X equals 180. And bottom line is, I get X is 52. So now we know that those are 52. I'm just going to save some time here. And since we know that this is a right triangle, that adds up to 180, I can find it. So 52 plus that 90 plus, we'll call this Y, has to add up to 180. And so if I solve that, I get that Y, or angle KSP, is 38 degrees. And there you go. Just kind of solving that a little quickly so we can get through the problems here. In the diagram below of parallelogram STUV, SV is x plus 3, VU is 2x minus 1, TU is 4x minus 3. What is the length of SV? Well, since it's a parallelogram, we want to figure out this. This has to be congruent to that. So we don't even need this. So we'd say x plus 3 is equal to that. X plus 3 is equal to 4x minus 3. So we solve that, and we get x is equal to 2. And then we plug it into SV. SV is x plus 3, so it's going to be 2 plus 3, which is 5. All right. Number 3, given the parallelogram, if DF is 5x minus 1, so this whole thing is 5x minus 1, what is XF? I guess this is x, so we want to figure out that. That's a question mark. Well, we know that XF has to be half of 5x minus 1. This is cut in half, and this is cut in half. Okay, and they give us these 2 halves, the 3x minus 5 and the 2x. So those have to be equal to each other. So we're going to do that first. For a parallelogram, the diagonals cut each other in half. So 2x is equal to 3x minus 5, which means x is equal to 5. And then we plug it into DF, which is the 5x minus 1, right? Plug that in there. 5 times 5 minus 1 is 24. And then XF has to be half of DF, so it's going to be 24 divided by 2. And actually, this should be a typo. That should be 5x plus 1, not 5x minus 1. So this should be plus 1, and that'll turn that into a 26, and then 26 divided by 2 is 13. So the answer is 13. Sorry about that typo. It should be plus 1, not minus 1. All right, so for number 4, says, using the same figure as in question 3, is EG perpendicular to DF? So let me erase all this. We want to see if these are perpendicular. Are these perpendicular, question mark? And the answer is, well, notice that this is equal to 26, right? And this is equal to, we said x was 5, so this is equal to 20. The red is 20, in total, and the black in total is 26. So they're not equal to each other, which means that this has to be a parallelogram, or a rhombus, or some kind of parallelogram, right? Which we can tell it's a parallelogram because the diagonals are not congruent, and they mention such. So it says here, no, the diagonals are not congruent, so it's not a rhombus. Well, that's actually not true. A rhombus does not have, in order to be a rhombus, the sides have to be the same length, right? And it has to be parallelograms. So the diagonals are never congruent in a rhombus, so this is not true. The diagonals are congruent, which we know it's not true, so automatically no. Yes, diagonals are always perpendicular in parallelograms. That is not true. They're only perpendicular in squares and in rhombuses, and that's not the case here. We don't know that this is a rhombus yet, right? They don't tell us. It's impossible to tell. They don't tell us that it's a rhombus. They don't tell us that, that these sides are the same, right? The FG is the same as DG and so on, and therefore we cannot tell. So the answer is D. All right, so for number 5, what angle would show that it's a parallelogram? Well, if it's a parallelogram, that means that these two opposite angles have to be congruent. So we're going to set them equal to each other and solve. That's it. Opposite angles are congruent in a parallelogram, and adjacent angles add up to 180. So if I solve that, I get Z is equal to 32. And then I'm going to plug it into DAB, which is this one. So DAB, let's call that W. We don't know what that is, but we do know that these adjacent angles, these two, this one and then this one, add up to 180. So we know that W plus that 2Z number, that 2Z plus 15, adds up to 180. And so then we can plug this in. So W plus 2 times 32 plus 15 equals 180. And bottom line, when we solve that, I'll have you show the work for that. You get W is 101 degrees. All right, which is the same as measurement of BAD. That's what we were looking for. Or DAB, same thing. All right, so number 6, using the same diagram as in 5, what values of x and y would show that it's a parallelogram? Well, if we want to show that it's a parallelogram, then that means the opposite sides have to be congruent. So let's go ahead and do that. These have to be congruent, these have to be congruent. So let's set up the equations. The 2x plus 4y has to be equal to the 3z minus 17. The 2y plus 3 has to be equal to the 3y minus 2. So let's solve that first. That's easier. If I solve this for y, bottom line, I get y is equal to 5. I'll have you solve that, just for the sake of time. Plug that in here. We got 2x plus 4 times 5 is equal to, that's not a z, that should be a y. Sorry about that, 3y. Hold on, let me check it real quick. Hold on. I wrote down the angle. No. So 2x plus 4y has to equal to 3x minus 3. Sorry about that. Just a little mistake there. Okay, so you plug that in there, we get equals to 3x minus 3. So you get 2x plus 20 equals 3x minus 3. I'll leave it to you guys to solve that for x. And you get x is equal to 23. So show your work to solve for x. I won't show it there for the sake of time. Let's finish up the last problem. Ms. Davis gave her students all the steps for the proof below. One step is not needed. Which step is not necessary to complete the proof? Okay, and there's the picture on the right. Okay, so step 1, let's see. ABCD is a parallelogram because that's given. That step is necessary, so you're not going to do that. You're not going to eliminate it. AB is congruent to DC. Let's go through all of this. AB is congruent to DC. AD is congruent to BC because it's a parallelogram. Okay, that's so good so far. Angle A is congruent to angle C. Okay, I don't know if we need that yet. BD is congruent to BD because of reflexive property. And so those two triangles must be congruent by SSS. So SSS. SSS. Okay, so there you go. They're congruent. And therefore, that means we don't really need these angles, do we? We only need SSS. And so we don't need angles. And so that's the step that we do not need. So the answer is step 3. All right. And let's finish up the last few problems here. We got 3 more problems here. What is the step in this final step in this construction? So here we're constructing a perpendicular bisector. All you got to do is connect those and make your perpendicular bisector. And how do we connect it? We connect it with a straight edge. So there you go. There's my answer, straight edge. And number 2, in order to construct the interior point of CAB, where should you place the compass point? Well, you should place the compass point in order to make an angle bisector, which cuts the angle in half. I need to figure out where that point is. And so that point has to be the same distance from C as it is from B. And so I have to place the compass from C to that point, and then from B to that point. Okay, so it's going to be, the compass is going to be placed on B and C. All right, go back to those steps for constructions if you want to review. What statements describe the steps to copy XY? Okay, so to copy XY, you need to place the compass. You need to measure that with the compass. And then you need to make a straight line with a straight edge. And then and mark that, say, I don't know, Z or something like that, whatever you want to label that. And then use the same measurement here to draw an arc. And then label that point W or something like that, okay? And then erase everything else, and then you're left with this line. So that's the overall steps of how to do it. So use a ruler. No, you don't want to use a ruler, just a straight edge. You don't have to use a ruler. It's a general straight edge. I guess they labeled it point M here. Doesn't really matter. And use a compass point. Open the compass to length XY. Yes, you want to open it to length XY. Using the same setting, place the compass at point M, draw an arc through line L. So there you go. That's what I did there. So that's true. With a setting greater than half XY, no, not half XY, XY. There you go. That's it. All right, that's going to do it for the video, guys. This is a very long video, but we covered the 13 pages for part 1. We'll finish up part 2 in another video. Thanks for your patience, guys. I hope you learned a lot of things. As usual, see you in the next one.